So I asked you to label your periodic table, and there's another page too, page 21, or let's make sure, yeah, page 21, that has a blank one that you can practice on. But group 1 is the alkaline earth metals. And remember that the groups are vertical and the periods are horizontal. So these families are vertical. So group, I just mislabeled it.
I'm like, wait a minute. I wasn't paying attention or something.
No, I wasn't paying. I was talking and not thinking. This is alkali metals. Your lithium, your sodium, your potassium. Those are your alkali metals. So thank you. Alkaline earth, group 2. That looks better. Then group 7 is your halogens. Group 8 is your noble gases. A lot of times students will confuse alkaline metals and alkaline earth metals, which I just did. So use that as a cautionary example. The way I always remembered alkali metals and alkaline earth metals, alkali metals is 2 words. Alkaline earth metals is 3 words. So the lesser number of words goes first. Or I'm sure you guys can come up with something too. Be careful with halogens and noble gases. So a lot of times, and students will think noble gases are halogens or vice versa. So on the next page, I'll go through a few practice problems to give you an idea of what's expected of you for this section, because it just seems like, well, this is so easy. I'm not sure why we're spending time on this, especially just coming off of conversions. But if I say, tell me what element is a halogen in period 4. So a halogen, so you'll have to look at your actual periodic table. Yes, bromine. So this is, I'll show you on. So my periods, this is period 1, 2, 3, 4, 5, 6, 7. Halogen is group 7. So when I say period 4 halogen, you're absolutely right. That's bromine. So that's bromine. If I said, I want to know what a noble gas is in period 3. So a noble gas, period 3. So my period, argon. There we go.
I think the noble gas is like really unsteady too, so you can kind of think of it as like
They're called inert gases too. They're not very reactive. So they're very stable.
Oh, they're very stable.
Yeah. So
I
you're.
couldn't remember which way they were.
Yeah. So they don't do very much. In fact, they're used to run reactions in. That if you'd run them in just air, then they would react with the water in the air. So if you need a dry atmosphere, you'll use a noble gas. So when I was in research in graduate school, we were working with phosphorus, which was really sensitive to water. So we would use argon as that's where we'd run all our reactions. So they don't like to react with much. And we'll talk more about that in Unit 2. Let's see, I'll give you one more. Transition metal in period 3. Or period 4, sorry. Period 4. Any transition metal in period 4. You can come up with iron, cobalt, nickel, copper, zinc. So you could come up with a lot. Nickel, copper, zinc. So a lot of different possibilities. But I wanted you to get an idea of what I'm looking for. So it's not just, there will be questions that are more specific than, what is group 2? That type of thing. Questions on this? So now we're going to get into atomic structure. And if you've had some chemistry, you've probably covered this. But if you think about elements, so elements are the pure form of something. You can't get it any simpler than an element. So if you think about having aluminum foil and you keep cutting it and keep cutting it, keep cutting it as small as you can. These are excellent scissors, right? You just can cut it as small as possible. Would you reach a point where you couldn't cut it any smaller? Yes. So what point is that when you reach that? 1 atom. So that's the building blocks, these elements. So yes. So an atom is the smallest and simplest piece an element can be divided into. So the smallest and simplest piece an element can be divided into. And I want to point out that it can still be identified by its characteristics. So each element behaves differently. So with 1 atom of a particular element, you can still identify it based on how it behaves. So, and still be identified by its characteristics. So within the atom, there are subatomic particles. There's the proton, the neutron, and the electron. The masses are given, and you'll see, bless you, these are in grams. These are very tiny amounts. 1.672622 times 10 to the negative 24. So it's a pain to keep track of these masses in grams. So we express them in relative masses relative to each other. So the mass of a proton based on the carbon atom is 1.07276. It's easier just to say approximately 1. 1.00. Now the charge on a proton is +1. The neutron has mass, and if you look at these masses in grams, you can see that the proton and the neutron are the same magnitude, -24. The electron is not the same magnitude, -28. So again, the neutron, you can take your answer out very far, but it's approximately 1. The charge on a neutron is 0. So a neutron is neutral. So there is no charge. Now an electron has a mass, a relative mass of 5.48 times 10 to the negative 4, let's call it. And what we do with that is we say that it's negligible. It doesn't really contribute to the mass of an atom. It's the protons and the neutrons that contribute to the mass, while the electron is approximately 0 mass. So no 0 mass. Now the charge on an electron is negative 1. So now we'll talk about how these subatomic particles are oriented in the atom. So protons and neutrons are in the nucleus. They both have mass, while electrons surround the nucleus. So in the nucleus you find the protons and the neutrons, and then these electrons are just spread very far apart. They don't like to be near each other. So the nucleus of an atom is very small compared to the size of the actual atom. So if the atom were a large dome stadium, the nucleus would be the size of a pea. So that just gives you an idea of how much space these electrons fill. So if you think about when the sun is coming through the window and you can see dust, you say, gosh, I really need to dust here or dust there when the light's just right. A speck of dust, how many atoms do you think a speck of dust contains? A lot. About 1,000,000 atoms in that one speck of dust. So that gives you an idea of just how small atoms are. So 1,000,000 atoms. So you always hear that saying, opposites attract, right? Sometimes you get tired of it. That doesn't always work. But it does in chemistry. So when you think of opposites attracting within the atom, what subatomic particles would be attracted to one another? The protons are attracted to the electrons. And this is kind of the glue that keeps this atom together. Those electrons don't want to get too far apart from the protons. They can be pretty far apart, but they still stick around because they're attracted to the protons. So this is just an overview of atomic structure. Our objective was just to describe the electrical charge, mass, and location in an atom for a proton, neutron, and electron. So now we're going to get to the fun part of working with the protons and the neutrons. And this is where your periodic table will come in handy. You'll really start to see why having a periodic table around with these problems is very useful. So when you're talking about an atom, say an atom of aluminum versus an atom of copper, for instance, they're different. Copper behaves differently. It's a different color. Aluminum's a different color. What makes it different is the number of protons they have. Now remember the protons, what charge does a proton have? Plus 1. Very good. Does it have mass? Yes. So protons are the kind of defining characteristic of each element. So carbon has 6 protons. If you look on your periodic table, and you look up carbon, what's the symbol for carbon? C. Now, in some chemistry classes, they will give you periodic tables that just have the abbreviations for the elements. They won't give you the ones that have the words written underneath. But in our course, we will always give you this periodic table. So if you panic, you can always read what's underneath it. So carbon, on your periodic table, has a lot of numbers written by it. You think, oh my gosh. We will actually learn a lot of these numbers, and they won't be so intimidating. But the number that I'm looking for, I'm asking you on this note page, what number is listed next to carbon on the periodic table? This is the number in blue right here, number 6. That is carbon's atomic number. So carbon has a 6 next to it. That is the atomic number. So I'm going to put it's in the bigger number. I'm going to zoom out so you can see what I'm writing. Bigger number written in blue. The atomic number tells how many protons and how many electrons are in an element. So this tells the number of protons and the number of electrons. So for this portion of our course, Unit 1, the number of protons and the number of electrons will be equal to each other because we're working with neutral atoms of a given element. Sometimes you will see Z written for the atomic number, like if we give you a quiz question or an exam question, we'll say carbon, and then in parentheses, Z equals 6, and then the question will go on. The mass number, the abbreviation for this is A. This is the sum of protons and neutrons. So, on the periodic table, back to carbon, there's the atomic number here. And if you look at the key on your periodic table right here, the red number is the atomic weight. And there's the atomic weight for carbon. You think, well, she just said mass number. She didn't say atomic weight. We will always ask you for the mass number. The atomic, we'll get into this, the atomic weight is kind of like an element's grade. And it has different weights for different isotopes. And we'll get to isotopes in just a second. But so it's not going to be exactly a whole number for the mass number. So for carbon, what is the mass number for carbon? The mass number isn't given on the periodic table. The atomic weight is given on the periodic table. So I have to provide you with the mass number, or I have to provide you with the number of protons and the number of neutrons so you can calculate the mass number. Does that make sense? Okay, so the mass number, not on the periodic table. So this question should say, what is the mass number for carbon 12? So, what is the mass number for carbon 12? But then you say, well, what does that 12 mean? That 12 is the mass number. And it has to be given to you. Like I said, the periodic table has the atomic weight. And we'll get to isotopes in a second. But a lot of times students want to say, on the periodic table, I'll just take that atomic weight off, and that's the same thing as the mass number, and it's not. So what is the mass number for carbon 12? It's given here. So from this, now you can figure out how many neutrons are present in carbon 12. So if I have the mass number, so remember that mass number, which is A, is the sum of the protons plus the neutrons. So I have 12 here. How many protons are in carbon? 6. Excellent. So I'm trying to solve for neutrons. So how many neutrons are in carbon 12? 6. So the neutrons equal 6. So I have to provide you with the mass number, or I have to provide you with the neutrons, at least. You can get the atomic numbers off the periodic table. Those, that tells you how many protons there are. So here's another question that covers this. Fluorine has an atomic number of 9, and you can verify this. Look at your periodic table. Right there. The atomic number 9. And a mass number of 19. How many protons, electrons, and neutrons are present? So how many protons does it have? 9. How many electrons? 9. How many neutrons? 10. Because it's 19 minus 9 gives you 10. 10 neutrons. So I'm taking A, so the mass number minus the atomic number gives you the number of neutrons. So oftentimes we will give you a table for a quiz or an exam. We will give you enough information so that you can piece it together. For instance, if I didn't give you the mass number on this first one, it would be hard to tell me how many neutrons there were, or the mass number. So I want you to work on filling out this table. And remember that the number of protons tells you the element's identity. So like 17, if you look on your periodic table, chlorine, 17 is chlorine. So, it seems really intimidating at first, like you have this whole table to fill out, but you guys can get this. You've gotten through conversion. This is, I can do this. So then, well, if you know the number of protons, then you must know the number of electrons. How many electrons are present in chlorine? 17. Well, that also tells you the atomic number. What's the atomic number? 17. And then what's the mass number? How would I figure that out? 17 protons plus neutrons. 17 plus 18, 35. So that's the mass number. Now if you look on chlorine, so but this mass number is not right. You're incorrect. Remember, this red number is not the mass number. It's the atomic weight. Totally different. So do not use these red numbers to get the mass number. And I'll probably say that about 5 or 6 more times just to clarify this. So go ahead and fill out the rest of the table. All right, so the first element is what? Iron. And the atomic number is the same as the 26, which is the same as the electron. So, and then to get the neutrons, what did you have to do? Subtract. So 56 minus 26 gives you 30. All right, the third entry is what element? Silver. Good. So the atomic number is the same as the protons, which is the same as the electrons. The mass number is going to be the protons plus the neutrons. So it's 108. The fourth entry, what element are we dealing with? Aluminum. So again, the electrons are the same as the protons, which is the same as the atomic number. The mass number is the protons plus the neutrons. So you get what for that? 27, that's right. And then the last entry, what element is it? Phosphorus. Good. So atomic number is the same as the protons, which is the same as the electrons. And then the neutrons is just 31 minus 15, so you end up with 16. So pre-lab 4 has a lot of these similar questions. So now you can do this. It won't look so foreign to you. And this is some of the easier portion of Unit 1. So, sometimes it's hard when you know it's easier because you don't really pay that much attention to it. I need to focus just on conversion factors. Don't completely ignore this because these are good gimme points. There will definitely be questions like this on the exam. And make sure you know how to fill it in because it will benefit you. Any points you can get will help you. Questions on this? Okay. All right. So now we're going to talk about isotopes. And really, filling out any tables is the same way for isotopes. So remember that we talked about atoms within an element have the same number of protons. The Z is characteristic. However, the number of neutrons can vary. So if the number of neutrons can vary, what else will vary? A, the mass number. Because remember, A is the protons plus the neutrons. So mass number, protons plus neutrons. So isotopes have identical atomic numbers, but they have different mass numbers. So for each element, there can be several isotopes that exist. Hydrogen has 3 isotopes. It's hard to predict how many isotopes a given element will have, but they do exist, and there's a certain percentage of what is naturally occurring, but we don't get into this. In other chemistry classes, you might have gotten that far into it. So for hydrogen, there are 3 different isotopes. What would the atomic number be of all the different isotopes? 1. So you look, but right beside hydrogen, and you see the number in blue is 1. So that's the atomic number. So hydrogen, 1, the mass number, and I should just write this there. The mass number is 1. The number of protons would be how many? 1. How many electrons? 1. And how many neutrons are there? 0. It's pretty strange, isn't it? But that's how it works. Now, an isotope called deuterium. You might have heard of deuterium. There are a lot of experiments in biology where they've used deuterium. Water, heavy water, they call it. So instead of using H2O, they use D2O. It's very neat. We found out a lot of things with the existence of these isotopes. But hydrogen 2, the mass number, when you're dealing with isotopes, is written second. So the mass number for hydrogen 2, or deuterium, is 2. Hydrogen 3, the mass number would be 3. So for deuterium, the number of protons would be how many? 1. The number of electrons would be 1. How many neutrons? 1. Good. 1 plus 1 gives you 2. You can always go back and double check yourself. Tritium has how many protons? 1. How many electrons? 1. How many neutrons? 2. So you're doing the same thing that we just did. It's just isotopes. You're dealing with isotopes. We are going to see this abbreviation coming up in our next set of lectures, where you have the element and the element abbreviation. This is the 1-letter or 2-letter abbreviation that you see on the periodic table. And then in the upper left-hand corner is the mass number, and the lower left-hand corner is the atomic number. So uranium 235. What's the mass number on uranium 235? 235. And I'm going to give you this atomic number because you wouldn't find it. It's in the inner transition metals, and I'll tell you specifically. It's in the actinides. Yeah, it's an actinide 92. Very good. So atomic number 92. So the way you will write the abbreviation for uranium 235 is 235 92. And I've always thought this was really neat. And, it looks so different from the writing that you see. And, like if you want to impress your friends with chemistry work, we'll be doing some equations with these coming up. And it looks really complicated, but it's just adding and subtracting. And, you think, oh, I can't get this. But it's just adding and subtracting. But that's our next lecture. Okay, so I've touched on this. Most naturally occurring elements are a mixture of isotopes. Atomic weight represents an average, including the isotopes. This is why hydrogen's atomic weight on the periodic table is a little greater than 1. So if you look, it's not exactly at 1 because there's naturally occurring deuterium and tritium that is found. So the mass number would be 2 and 3 for those respectively. But again, this number in red on your periodic table is not the mass number, it's the atomic weight. Questions on that?
Just real quick, those isotopes, is that kind of where you get into like nuclear decay?
Yes, and we're going to get into nuclear decay. All right, it's fun stuff. It looks really intimidating, but it's adding and subtracting. Chemistry and fun in the same sentence. Yes, you can have that. All right, so I want you to fill in this table on page 26. It's pretty much the same thing you just did, but you're getting better at it because you've seen it a few times now. If you wanted to, you could have written out the element name and then the mass number after it, like boron 12. But I want you to know that when you see an element written with like carbon 14, that second number is the mass number. But either you could have just put the element or, you know, written it out like they had, or you can even go like CL36, CL37, P32, O16. A lot of times if you work with these isotopes over and over again, you start saying P32, C14, C13, that type of thing. But I wanted to point out these examples. Chlorine, you know, they have the same atomic number, same number of protons, same number of electrons, but they have a different number of neutrons, and that makes them isotopes of one another. They have different mass numbers too. Any questions on this? So practice this. Pre-lab 4. Yes, you have.
Are you going to count out on the exam if you do not put like the 37 or 32?
No, I wouldn't count. If you left off, unless I specifically said what, you know, put it in this format. But no, I wouldn't count off for that. I think right now it's kind of unclear the way I have this table written.